Hi folks, my name is John O'Reilly. I'm based in Galway, in the west of Ireland. I work remotely for a London-based company called Kraken Technology, part of the Octopus Energy Group, not the crypto company, by the way. It's a pleasure to be here at KotlinConf in Copenhagen today. So we're going to talk today about various patterns and capabilities that we can apply when using Kotlin and Compose Multiplatform on iOS. We'll start by giving a basic introduction to the ecosystem and talk about the default Swift Kotlin interop we get out of the box. This has a number of limitations, and we'll then cover the capabilities that the SKIE framework provides to address those. We'll also touch on the new Swift export functionality that JetBrains is also developing to improve that interop. Next up, concurrency. Again, we'll talk about the limited interop support we get by default and the third-party solutions we can use for this. Including use of Swift in shared KMP code is something we often need to do, and we'll demonstrate some patterns for how that can be achieved, along with other interop options available to us for accessing native iOS capabilities. And similarly then for Compose Multiplatform, showing, for example, how we can include use of Compose in SwiftUI and vice versa. We'll also talk a little bit about background work on iOS, some of the KMP, CMP testing options available to us, and a few items related to developer experience. We'll then finish up with some info on the build, packaging, and publication of KMP-based iOS apps. So starting off with a few basic definitions, just to level set. This is how KMP is described in the official docs. It's basically providing a mechanism for writing shared Kotlin code that can be built and run natively on a wide variety of platforms. So first, usual show of hands. How many people here have used KMP? OK, wow. Hopefully, probably not too unexpected these days that there's so many. Next up, Compose Multiplatform. As folks already know, this is a declarative UI framework for sharing UI across multiple platforms. It's based on Kotlin Multiplatform and Jetpack Compose. Another quick show of hands. How many people here have used CMP? OK, good number two. It's great to see that. And as mentioned in the keynote yesterday, very cool to see that CMP for iOS is now stable. Just to mention at this point that many of the examples shown in the talk today are taken from various KMP and CMP samples I've been working on, along with other folks over the last 6 years. These all include iOS clients and also have varying degrees of use of shared Compose Multiplatform UI. Collectively, they cover a range of different code sharing scenarios. I'll also touch on some examples we're using in a Compose Multiplatform application we're developing at Kraken. So with KMP and CMP, we have an almost continuous spectrum of code sharing possibilities. I wanted to show here a few points along that spectrum. On the left, we have a small amount of shared KMP code, along with a SwiftUI client and Swift view model, for example. In the middle case, most of the logic is shared, including the view model, with potentially some shared CMP UI code, maybe a particular screen or just some part of a screen. And finally, on the right, we're sharing most of the code, including the UI using CMP, with potentially some SwiftUI as needed. It's important to note that our interop requirements vary considerably depending on what point along this spectrum we're targeting. OK, we're going to focus now on the development of iOS apps using KMP. And a key component of the Kotlin toolchain that supports that is Kotlin Native. It's described as a technology for compiling Kotlin code to native binaries, which can run without a virtual machine. It includes an LLVM-based backend for the Kotlin compiler and a native implementation of the Kotlin standard library. It also importantly provides bidirectional interoperability with Swift Objective-C. You can both use Objective-C frameworks and libraries in Kotlin code and Kotlin modules in Swift Objective-C code. And what this typically means in an iOS project is that an iOS framework is generated from our shared Kotlin code. And that framework can be consumed then in an Xcode project, for example. Also, an important aspect of this solution is that interop between Swift and Kotlin is currently based on an Objective-C bridge. This is an evolving area, and with the development of Swift export by JetBrains, we'll hopefully soon have direct Swift Kotlin interop. So in most KMP projects, we'll need to access platform-specific capabilities. And a key component for allowing that is the expect actual mechanism. We can expect a particular API, et cetera, to be available in common platform-agnostic code, and provide then the necessary platform-specific implementations for that. And how we manage that then is through various source sets in our KMP modules, with common main for our platform-agnostic code, and then platform-specific source sets for each platform. So first, small expect actual example. Here we have a get country name expect function that we can invoke in common main code. And we have then actual implementations for Android and iOS in their respective source sets, using locale on Android and NS locale on iOS. So a quick random spot quiz. Anyone here know what the NS prefix stands for in the NS locale API we're using here for iOS? Yeah? Should anyone shout out? Okay, close. So a little aside. After Steve Jobs left Apple in 1985, he founded a new company called Next, which developed the Next Step operating system. In 1997, Apple acquired Next, along with getting Jobs back, and that OS ultimately became the basis for what would become Mac OS and iOS, etc. And I find it interesting that today we see that legacy manifested in Kotlin KMP code. So back to our regular schedule program. Another spectacular example, this time showing how we can create platform-specific dependencies when using the CoinDI framework. We have a common coin module, and then a module specific to each platform, again using expect actual. And in the iOS case here, for example, we define platform-specific dependencies for Ktor, Data Store, and Room, which all have KMP libraries now. And this is how that create data store is implemented for iOS. The specific details aren't too important, but just to note again, we have access to the likes of NS File Manager to allow us to interface with the iOS file system from Kotlin code in iOS main. Also important to note that we can use the same mechanism for compose code, as we'll see in more detail later. Here we have this ISS map view expect function that we can use in common main, with actual implementations then for each platform. So the default and the ideal is to have any shared iOS-specific code in the iOS main source set in our KMP modules. We'll be talking, of course, about some cases where that isn't sufficient, but important to note that Kotlin Native comes with a large set of pre-imported iOS system frameworks that we can call from Kotlin code in the iOS main source set. So just to give a few examples of some of the default Kotlin Swift type mappings we get when using Kotlin Native. Again, through that Objective-C bridge. Class in Kotlin maps to class in Swift with interface mapping to protocol. And Interop using these is quite seamless. Where we start to see some disconnect is with sealed classes, for example, with some functionality lost in the default mapping to a Swift class. For example, exhaustivity checking. And we'll talk shortly about how this and other disconnects can be addressed using third-party solutions. Just showing here then the mappings for some of the basic types. Again, these map quite seamlessly. And lastly, some examples of collection types being mapped. Kotlin list to Swift array, set to set, and map to dictionary. A small example then of calling KMP code that returns a Kotlin list, which can then be assigned directly to a Swift array. The mapping is a little less straightforward if you need, for example, to pass a collection from Swift to Kotlin, but there are ways to do that. We mentioned some of the disconnects that exist when using the default approach for mapping between Kotlin and Swift. And one popular third-party solution that's emerged to address this is SKIE, standing for Swift Kotlin Interop Enhancer. It's one of a suite of solutions that TouchLab have developed for KMP that have become indispensable. Included in what SKIE provides are supports are enums, sealed classes, as we mentioned earlier, default arguments, global functions, overloaded functions, and coroutines interop, which we'll talk about in more detail in the concurrency section later. So, starting off with the example of sealed classes. These are, of course, quite an important part of the Kotlin language, frequently used, for example, for encapsulating UI state as shown here. And a key aspect of what they provide is exhaustivity checking, which we don't, as mentioned, get in the default mapping that Kotlin Native provides. With SKIE, this onEnum function is automatically generated for us, which allows that check to occur. And we see it here, for example, in Xcode, if we try to remove one of those cases, resulting in this switch must be exhaustive error. Another small example is global functions. Without SKIE, we have to prefix this function in Swift with the Kotlin file name. SKIE removes the need for that. I mentioned earlier that existing Swift Kotlin interop is done through an Objective-C bridge. With Swift export, JetBrains is working to provide direct bindings. It's very exciting to see that develop. And as announced in the keynote yesterday, all the features shown here will be available in the upcoming Kotlin 2.2.20 release. Also, this talk was on just before this, and definitely recommend watching it if you haven't done so already. Artem also mentioned, by the way, that coroutines interop would be the next in the roadmap after the 2.20 release. And speaking of which, next up is concurrency. So just to start off by giving some basic background on the structured concurrency functionality that we now have on Android and iOS, before we talk about interop between them. This is a really powerful capability that allows us to write async code in a way that's easy to read, and also allows a more deterministic, structured approach to error handling and cancellation, for example. A key enabler of this is the ability to have code that can be suspended at particular points and resumed later. Swift supports these capabilities through the likes of tasks, async functions, and async sequence, and Kotlin similarly through coroutines, suspend functions, and flows. And a very important aspect of this approach is how invocation of code like this can be tied into the UI lifecycle, thus allowing, for example, automatic cancellation when a view disappears. So just a few small examples of how we would invoke async code in Swift and Kotlin. We can invoke from a function that's marked as async in Swift or suspend in Kotlin. We can also create a specific task in Swift, and similarly in Kotlin, create a coroutine from which the code can be invoked. We can also tie invocation of async code to our UI lifecycle on both platforms, along importantly then with automatic cancellation when the UI is no longer shown. We can use the task view modifier in SwiftUI for this, and can also use, for example, launched effect in Compose. And showing examples of async sequence in Swift and flow in Kotlin. We use for await in Swift to iterate over the values, and use collect in Kotlin to do the same thing. And then also a few examples of some of the operators supported. Firstly, using map in both Kotlin and Swift to convert each value to its uppercase version, and again iterating over the results. And then filter to, for example, filter on a particular string, again in a very similar manner. Okay, now I'm going to talk about some of the concurrency interop options we have available to us. We'll briefly cover the limited interop default behavior we get out of the box with Kotlin native, and then talk about a few third-party solutions that have become established to support this interop. So by default, Kotlin suspend functions are represented as Objective-C methods with completion handlers, or callbacks, which can also be called from Swift as async functions since Swift 5.5. These do have some important limitations, though, such as, for example, the fact that cancellations are not propagated. Not going to focus too much on this approach, as there's third-party solutions that are generally used these days to provide concurrency interop, as we'll see shortly. Just to mention that the official guidance from JetBrains is also to use these third-party solutions, such as KMP native coroutines and SKIE. And as mentioned here, both of these libraries support proper cancellation of coroutines. By the way, we're focusing here on interop with the Swift structured concurrency capabilities added in Swift 5.5, as they map quite nicely to how structured concurrency works in Kotlin. There are also, through these libraries, ways to support other iOS concurrency frameworks, such as Combine and Oryx Swift. First of these alternatives is KMP native coroutines library. It was one of the first solutions created that provided interop for both suspend functions and flows, along with providing that cancellation support. For suspend functions, we annotate our Kotlin functions with @native coroutines, and then in Swift use the library's async function to invoke, and can use then with Swift's await. Likewise with flows, in this case using the library's async sequence function to convert the flow to a Swift async sequence. I could then use Swift's for await in this case to iterate over the values collected from that Kotlin flow. Next up is KMP observable view model, from the same author, by the way, as KMP native coroutines. This is a library, by the way, that was previously known as KMM view model. It's now described as a library to use Android X Kotlin view models with SwiftUI, given the availability now of KMP version of the Jetpack view model library. And a key aspect of what this offers is the ability to expose Kotlin state flows, for example, as Swift properties that can be directly observed in SwiftUI, as we'll see next. So this is an example of one of the shared Jetpack view models in the bike share KMP sample. In this case, exposing the list of countries we're displaying. We're using our repository class to get the list of countries, doing some transformation of that information, and exposing then as a state flow. And this is how that's consumed in SwiftUI in the iOS client. We instantiate the view model we saw in the previous slide, using the @state view model property wrapper provided by the KMP observable view model library, which then allows that country list state flow from the view model to be observed directly here as a Swift property. And any change to that will cause our UI to be recomposed. As with KMP native coroutines, SKIE also supports concurrency interop with Kotlin. Showing again here how we'd invoke a Kotlin suspend function from Swift. With the approach that SKIE is taking using KSP, it can provide a more seamless interaction from Swift, as we can see here, with no additional wrapper function needed. And then likewise for consuming Kotlin flows from Swift. We have a Kotlin state flow shown here, and can then use Swift's for await to collect the values from it. Another related piece of functionality that SKIE provides is the ability to observe Kotlin flows in SwiftUI, as if they were Swift properties. Quite similar to functionality provided by that KMP observable view model library, for example. Here, we're observing in SwiftUI the UI state flow from our Kotlin view model. And again, the UI will be recomposed if that changes. Next up, we're going to outline some patterns for using Swift in shared Kotlin code. So a key enabler for this is the ability for a Swift class to subclass a Kotlin interface, and that implementation then to be passed to and used from shared code. And this approach is the basis for most of the interop scenarios we'll be describing. Starting off with a small example from the Firebase Vertex AI sample I have. You may have seen this in the JetBrains booth, where it's being used to demonstrate this pattern as well. So this is a composed multi-platform application with most of the code shared between Android and iOS. The screenshot here is from the iOS app. Here we have an interface, generative model, defined in common main in our KMP module. And in this case, being used to generate images using the Vertex AI SDK. By the way, the observant of you might have noticed that it managed to somehow misspell Kotlin on the t-shirt, which is interesting. And this is the implementation on Android, using the associated Firebase Vertex Android Gradle dependencies. It creates an image model using that library, and from that generates an image using the supplied prompt. And we can implement that same Kotlin interface in Swift code, this time making use of APIs from the Firebase Swift package to do the same thing. Note we're using SKIE here, which makes the concurrency aspect of this quite seamless. We override the suspend function in the Kotlin interface with an async one in Swift, and can use Swift's await when invoking the Firebase APIs. We're also making use of a helper function in shared code to convert the results to a Kotlin byte array. And this example then of how we can provide that generative model Swift implementation to our shared KMP code. In this case, we're providing it when we initialize the CoinDI framework from Swift iOS code. And that instance then becomes part of the coin object graph, and is what is injected into our common code when running on iOS. And here we see that generative model instance getting injected into the view model in common main. Coin will inject the platform-specific instance of this, depending on the platform we're running on. And then showing compose code using coil to display the generated image. And again, this is in common code. Another common example is Firebase Analytics. Again, we define a Kotlin interface in shared common KMP code, along with an Android implementation in our Android main source set. Again, using the Firebase Android Gradle dependencies in this case. And then implementation in Swift. Note again that Analytics here is a Kotlin interface. And this is making use of the Firebase Swift package again. And again, we'll pass this instance to shared code, as we'll see next. In this case, we're using the Kotlin inject DI framework, passing in the Swift instance when creating the Kotlin inject component from iOS code. Using override here in that Kotlin inject component provides a similar mechanism to ensure that this instance becomes part of our object graph when running on iOS. And a small example here then from the Confetti sample using the decomposed component in this case. Here we're actually providing the Swift implementations as closures, which again we can use from shared code. Another interesting approach that's emerged recently is the Swift Package Manager for Kotlin Swift Package Manager for Kotlin Multiplatform plugin. It's quite a mouthful. It provides the possibility, in certain cases, of actually consuming the Swift package from iOS main code. Next, we're going to talk about some of the UI or interop options available to us when using Compose Multiplatform on iOS. We'll talk about how expect actual can be used again here for providing platform-specific implementations in shared code. We'll then give an overview of UI kit-based interop that's available, and how that forms the basis for allowing both consumption of Compose code in SwiftUI and SwiftUI code in Compose. By the way, for those that aren't aware, UIKit was the predecessor to SwiftUI, but was the primary UI framework on iOS when Kotlin Native was originally being developed, so still forms the basis for any UI interop. Firstly, use of expect actual. So often this interop is done already for you using this approach in the increasing number of CMP libraries out there. For example, this is code that's using the KScan barcode scanning library from Ismail Mohammed, a colleague of mine at Kraken. Under the hood, that library uses MLKit on Android and AV Foundation on iOS. That scanner view composable is defined as an expect function in common code. And then we have Android and iOS specific implementations, using, as mentioned, MLKit for the implementation on Android and AV Foundation on iOS. But again, consumers of scanner view writing composed code in common main are abstracted from these platform differences. Next up, UIKit-based interop. As mentioned, Compose Multiplatform is interoperable with the UIKit framework. We can embed Compose Multiplatform views within UIKit code, as well as embed native UIKit components within Compose Multiplatform. And by combining this then with SwiftUI's own UIKit interop, we can in turn provide a way to consume Compose code in SwiftUI and vice versa. A key component we're going to be dealing with when performing that interop is UI View Controller, a word you're going to hear me mentioning quite a lot in the next few slides. It's defined simply as an object that manages a view hierarchy for your UIKit app. So these are the key UIKit-related classes that Compose Multiplatform and SwiftUI provide to allow us to implement that interop, based on using that UI View Controller object as a bridge. For Compose Multiplatform, we have Compose UI View Controller, a CMP function that wraps Compose code as a UI View Controller, and UIKit View Controller, which supports the reverse, allowing inclusion of a UI View Controller in Compose view. And we have a similar symmetry in SwiftUI with UI View Controller representable, which allows including a UI View Controller in SwiftUI, and UI Hosting Controller for wrapping SwiftUI as a UI View Controller. Another view of these same classes here showing the interop options they enable, using SwiftUI's UI View Controller representable and CMP's Compose UI View Controller to allow consuming Compose code in SwiftUI. And similarly then, using CMP's UIKit View Controller and SwiftUI's UI Hosting Controller to allow consuming SwiftUI in Compose. So a lot of moving parts that will hopefully become clear as we work through some examples. So let's firstly look at an example of how we can consume Compose code in SwiftUI. This is our main SwiftUI view in this example. It includes Compose view, which is another SwiftUI view that will wrap around our shared Compose code, as we'll see next. By the way, it can be a little bit confusing going back and forth between Swift and Kotlin. So using the color of the border of the code block here to indicate which, with red for Swift, as we can see here, and purple for Kotlin. So, and that Compose view we mentioned in the previous slide implements SwiftUI's UI View Controller representable, which allows including a UI View Controller in SwiftUI code. And it does this by invoking main view controller, a Kotlin function we have in our shared Compose code, from this make UI View Controller Swift function. And this is that main view controller Kotlin function. And that in turn is using CMP's Compose UI View Controller to wrap Compose code and return a UI View Controller to the invoking SwiftUI code. And this approach is the basis for most scenarios where we want to consume shared Compose code in SwiftUI. Where things get a little more complicated is where we want to consume SwiftUI views in our Compose code. Just another quick show of hands. How many people are trying to do that or have been trying to do that? OK. A couple of lonely hands have gone up there. And this is usually enabled through use of a native view factory class. This is a Swift class that implements a Kotlin interface and is responsible for creating SwiftUI views that our CMP code can use. The general approach here is the same as we mentioned earlier for consuming Swift in shared KMP code, with an instance of that view factory being passed to and used from shared CMP code in this case. So going to illustrate this using this example from the People in Space CMP sample, where we're showing the position of the International Space Station in a SwiftUI map. Here we have an outer SwiftUI shell that just basically includes a title bar. That in turn uses Compose for the content area, which in turn is using SwiftUI for the map. This is somewhat of a contrived example, but is designed to hopefully clearly illustrate the various moving parts needed to support this type of interop. So the first part, consuming the shared Compose code in SwiftUI, is much the same as we saw in the earlier example. We have our outer SwiftUI view that in this case includes just a navigation view and a title bar. That view also includes Compose view, which, as we saw before, is a SwiftUI view which will wrap our compose code. And again, that view implements SwiftUI's UI view controller representable and invokes this ISS position content view controller Kotlin function that's in our shared CMP code. In this case, we're also passing down our view model and the native view factory instance we mentioned earlier. That Kotlin ISS position content view controller function then in turn, as we saw before, uses CMP's compose UI view controller to wrap the shared compose code, ISS position content in this case, as a UI view controller which can be included in SwiftUI. Note, we're using composition local provider here to ensure the native view factory instance we're passing down is available in the compose code that needs it. More about that shortly. And this is that ISS position content composable. It has some basic UI for showing the position of the International Space Station in composed text views, and also includes ISS map view composable, which will ultimately wrap our SwiftUI map. OK, now going the other direction. And just showing again the key components that allow us to consume SwiftUI and CMP code, using CMP's UI kit view controller and SwiftUI's UI hosting controller. And it's showing here that ISS position content composable again. As mentioned, it includes the ISS map view composable, which will wrap our SwiftUI map. And that ISS map view, in turn, uses CMP's UI kit view controller to allow including a UI view controller in compose code. It does that by using that's the Swift native view factory we passed down to create that UI view controller, which will in turn wrap the SwiftUI map. Note that the view model we passed down from SwiftUI is being passed back up. It contains the position information which we'll need to observe and show on the map. OK, we're nearly there. We're back up in Swift code again. And this is the native view factory and the create ISS map view function we just invoked from that compose function. That's going to use SwiftUI's UI hosting controller to wrap the SwiftUI map implementation and return a UI view controller that can be included in our compose code. And finally, we have that SwiftUI map view. Note, we're also using SKIE's observing here to observe the position information from our view model, which will show then on the map as it changes. Another approach you can take for this type of interop, in particular when using SwiftUI views in compose code, is compose Swift Bridge from TouchLab, which abstracts you from some of the details we just showed. OK, finishing this section with a small example of how common composed multi-platform adaptive layouts work equally well on iOS. This is the My Mac designed for iPad version of the Confetti CMP app. And you can see here a small example how we can easily use the CMP adaptive libraries to dynamically switch between different layouts depending on the screen size, switching between a list and a grid view in this case. Next up, I'm going to talk a little bit about how we can run background tasks on iOS in a KMP and CMP app. So there are two types of background tasks on iOS, BG app refresh task and BG processing task. BG app refresh task is typically for short duration tasks that expect quick results, whereas BG processing task is for tasks that might be time consuming, such as downloading a large file or synchronizing data. Just another quick show of hands, how many people have used background tasks on iOS? OK, nice, quite a few people. And as you probably know, just showing here how we firstly need to enable these capabilities in Xcode, and also how identifiers for any task we create need to be added to the info.p list. Starting off by showing an example of how we can run, say, a nightly refresh, triggered from SwiftUI using relatively new background task view modifier, but invoking then shared KMP code to do the work. When the app goes into the background, we schedule the refresh. That's done using the schedule data refresh method, using BG task scheduler to schedule the request. Note that refresh data string shown here is the identifier we added to info.p list. Very important to remember to add that. And then just showing shell of the shared Kotlin code that the background task is invoking. Another approach is to create and schedule the tasks in iOS main in shared KMP code. There's a very nice example of doing this in Chris Baines' TV sample, and we're also doing something similar for the CMP project we're developing at Kraken. Another useful API we can use in iOS main is begin background task with name. This allows us to mark the start of a task that should continue if the app enters the background. We also get notified if our remaining background time is running out, and can, for example, schedule a background task if that happens. Next up, we're going to look at some of the testing options available to us in KMP and CMP apps. These options include running KMP unit tests, CMP UI unit tests, Swift tests that invoke shared KMP code. I also wanted to show an example of a nice UI testing framework called Maestro that we can use to test both our Android and iOS CMP apps, for example. So first option we have is running unit tests in common KMP code from our common test source set. These can be run then for various platforms we're targeting. Note also that we can add, for example, an iOS test source set here if we want to run iOS tests that need to test code that's in iOS main. A very nice capability that we also have now is the ability to run CMP UI unit tests, again from common test, and also with option to run on different platforms. Another option yet again, then, depending on our requirements, is to run Swift tests that in turn invoke shared KMP code, as we're doing here in the confetti sample. Lastly, Maestro, a really nice UI testing framework that wraps around UI Automator on Android and XC Test on iOS. We can run this script for both iOS and Android CMP clients, for example, with option as well to run certain steps for each platform if needed. By the way, anyone here using Maestro right now? OK, a few people. Nice. And just a small example of a Maestro test running here with the Confetti iOS application. This test automatically scrolls to the session title we're looking for. Taps on it, asserts certain information is visible, and then navigates back. Next up, just a few items related to developer experience. Yet another TouchLab tool that I definitely recommend using is Xcode Kotlin. This is a plugin that allows browsing and debugging Kotlin code from within Xcode. Here we see, for example, a case where we've added Kotlin source to Xcode and have been able to set breakpoints in Kotlin code and view variables, etc. Really, really useful tool to have. Next, showing how we can view documentation that's in our Kotlin code from within Xcode. We just need to ensure we have this option enabled in our Kotlin build file, our Gradle build file rather, after which we're able to see the documentation as shown here. In this last section, we're going to cover some topics around the building, packaging, and publication of iOS apps built with KMP and CMP. So basically, there's two main approaches used for building and consumption of KMP shared code. The first one here is usually based on a single repository containing both the shared and the client code. In this case, we build the iOS framework directly and consume it within the Xcode project. And the building of the shared code as an iOS framework is triggered through an Xcode run script like this that uses KMP's embed and sign Apple framework for Xcode Gradle task. The other approach is typically used when there's separate teams for the client and the shared code, and usually involves separate repositories for each. Here, a Swift package is created from the shared code and published to a remote repository, along potentially with use of some cloud storage for the XC framework zip file that's part of the package. That package can be added then to an Xcode project using, for example, GitHub repository URL that the package is published to, as shown here, for example, with the BikeShare Swift package repo. The Swift package in this example for the BikeShare project was built using the Multiplatform Swift package plugin. This plugin automatically creates the associated XC framework and package.swift files. The publication of these artifacts, though, needs to be managed separately. Another solution that many teams are now using for this is KMBridge, or Cambridge as it's known, from, probably guessed it, TouchLab. This also creates the XC framework from the shared code, but also, importantly, supports a range of options for managing the publication. Very powerful tool. Next up, umbrella modules. Typically, we need to expose a single iOS framework. But what do we do if the shared code is split across multiple modules, as is frequently the case? The solution generally recommended here is to create what's called an umbrella module, for which a single framework is built, but includes code from other modules, as shown here. Now we're going to talk a little bit about the building publishing of iOS apps in CI. Folks might be familiar when using Fastlane for Android. But it also has a ton of really nice iOS-related integrations as well, and we'll show a few examples here. Another quick show of hands. How many people here are using Fastlane? OK, quite a large number as expected. What we typically want to do is build, sign, and publish the iOS app to App Store Connect, initially to test flight for internal and beta testing, and then to production. So Fastlane provides a nice action to build the IPA file that's needed for publication, as shown here. And then a task, for example, to publish that IPA file to test flight. An important requirement when building publishing iOS apps is, of course, how we sign them. And Fastlane provides a very nice option for doing this using the relatively new capability called Match. With this approach, we add our certificates and provisioning profiles to a dedicated private GitHub repository. And Match then provides a convenient way to both distribute these across a team and also use in CI. And a small example here then of using Match in CI to automatically sync certificates so they can be used as part of the build. So today we talked about various patterns and capabilities that we can apply when using Kotlin and Compose Multiplatform on an iOS. We covered the basic interop capabilities we get by default. These have limitations, and we gave some examples of how these can be addressed using the SKIE framework. And also mentioned about the promising Swift export work that's being done by JetBrains. Similarly with concurrency, again, we covered how a number of third-party solutions can be used to address the limited interop support we have there as well by default. Next, we outlined some various patterns we can use for including use of Swift in shared KMP code. And likewise then for Compose Multiplatform, showing various interop options available for including Compose and SwiftUI and vice versa. We talked about background work on iOS, some of the KMP CMP testing options available to us, and a few items related to developer experience. We finished up then with some info on build packaging and publication, again focusing on iOS aspects of this. Thank you very much.